Modern industrial security is facing a threat it was never designed to handle. Traditional defense doctrines are failing. In this video, we are analyzing a critical technical shift: how low-altitude, long-range autonomous drones bypass advanced radar networks and achieve precise terminal guidance under total electronic warfare conditions. No signals, no communication links, just raw processing power meeting physics. The primary vulnerability of any classic radar station lies in a fundamental law of physics: the straight-line propagation of high-frequency radio waves. Radar cannot see around the curvature of the Earth. To calculate the distance of direct line of sight for low-flying targets, engineers use a standard geometric rule. The distance is roughly equal to the square root of 2 times the effective radius of the Earth multiplied by the height of the radar antenna, plus the square root of 2 times the Earth's radius multiplied by the cruise altitude of the drone. If a radar station sits on a 30-meter mast, and the drone is flying at an altitude of just 20 meters, the absolute theoretical detection range is less than 38 kilometers. In reality, this number drops significantly due to a phenomenon called terrain masking. By utilizing riverbeds, valleys, and natural depressions, an autonomous system can stay entirely within the geometric shadow of the landscape. For a stationary radar, such an object remains completely invisible until it clears the final obstacle, often just moments before reaching the target. But staying low is only half the battle. The second layer of radar evasion is the incredibly small radar cross-section, or RCS, of modern composite materials. Built from fiberglass, carbon fiber, and structural epoxies, these long-range drones possess an RCS value between 0.05 and 0.1 square meters. Standard radar clutter filtering algorithms are programmed to ignore signatures this small. The system automatically classifies the return signal as a flock of birds or a dense rain cloud, filtering it out of the tactical display to prevent overwhelming the operators with false alarms. The drone essentially uses the radar's own software logic against it. What happens when an autonomous drone enters an area protected by heavy electronic warfare? The onboard navigation boards register total degradation of all satellite constellations. GPS, GLONASS, and Galileo signals vanish. The system enters a state of blind inertial flight. A standard, low-cost inertial measurement unit, or IMU, relying on micro-electromechanical gyroscopes, immediately begins to accumulate a positioning error known as drift rate. Without external corrections, the drone's calculated position will deviate by hundreds of meters for every kilometer traveled. To solve this without using vulnerable radio signals, modern automated guidance systems look down. This approach utilizes an industrial evolution of terrain contour matching, or TERCM, paired with its visual counterpart, DSMAC, which stands for Digital Scene Mapping Area Correlator. Before launch, a compressed array of high-resolution satellite imagery, known as the reference map matrix, is flashed onto the drone's solid-state drive. During flight, a downward-facing digital camera continuously captures the terrain below. The onboard processor then executes a multi-stage computer vision pipeline. First, a canny edge detection filter extracts structural shapes from the live feed. Next, feature tracking algorithms like SIFT or ORB isolate key landmarks. Finally, the system calculates a homography matrix, aligning the live video frames with the stored satellite reference data. This process creates a continuous chain of visual odometry. The system determines its exact coordinates based entirely on what it sees, without transmitting or receiving a single watt of radio energy. You cannot jam an algorithm that simply looks at the ground and calculates its own physics. The final phase of an autonomous flight is the most demanding. In a zero-connectivity environment, a drone cannot rely on a human operator for remote targeting. The task of object recognition and precise impact calculation must be handled entirely on the edge. This requires high-efficiency, low-power hardware, such as Edge AI tensor processors from the NVIDIA Jetson or Halo architectures, running directly inside the drone's avionic bay. As the system approaches the target area coordinates, the onboard neural network, which has been pre-trained on thousands of synthetic 3D models of industrial architecture, activates its target recognition pipeline. The algorithm is not searching for a GPS coordinate. It is looking for a specific geometric signature. The structural proportions of large fuel tanks or the high aspect ratio cylinders of distillation columns represent unique spatial features. The Edge AI model detects these bounding boxes, estimates their 3D orientation, and calculates the exact spatial center of mass for the critical asset. Once the target is verified, the autopilot closes the feedback loop. The error vector between the target center and the drone's trajectory is converted directly into servo commands for the control surfaces. The drone enters its final dive. The terminal angle is computed to exploit the weakest structural point of the facility, ensuring that the kinetic and thermal energy completely disables the production line for months to come. The democratization of edge AI and passive optical guidance has fundamentally rewritten the rules of industrial asset protection. Security is no longer about the power of your radar transmitters. It is about the sophistication of your passive detection algorithms. Subscribe to the channel. In our next analysis, we are breaking down the structural vulnerabilities of cooling infrastructure inside hyperscale data centers. See you next time.